Hi, I'm Reno Jose, and I created the Forthic programming language to help me build tweakable applications for program managers at LinkedIn. Before we talk about how to use Forthic to solve problems, I'd like to talk about why I created Forthic by describing why other programming languages were created, in particular the ones that have influenced me. We'll cover these in the order in which they appeared, because every language was influenced by and a reaction to the programming languages that came before them. So let's get started. So the very first programming language it was Fortran. And I know we're reaching back a ways, but people are still using it. I learned it in college, and I wrote programs in it. I continued to use it in graduate school and wrote programs in it then too. And so, it's still relevant and still very important. It was released in 1956. It was initiated by a memo that John Backus wrote in 1953. And he wrote this to his boss at IBM. And, at the time, we just had machine language. And so people like John von Neumann, geniuses, we still use the von Neumann architecture for most of our computers. He had no problem writing in machine language, and so he's like, okay, fine. I don't see why you need it, but go for it. And what John Backus wanted was for the non-geniuses that struggled writing programs in machine language, in particular, translating numerical algorithms that were written in mathematical notation into machine language. He wanted to create something that would make that a lot easier. And he wanted to create something that was safer and faster. And by creating a higher level language that could run on top of different machine architectures, you could essentially write a program once and then run it on different machines, and which that wasn't possible in the 50s. So Fortran was really the very first abstraction above the hardware, above the machine language. And its domain, as we mentioned, was numerical algorithms. And in this, it is still unmatched 70 years later. All of the classic Fortran numerical libraries are still at the heart of large-scale simulations and big data science applications today. So it was way better than machine language. The second programming language, the second true programming language, was Lisp. And so it had to answer the question, why not Fortran? We have Fortran, why not use that? This first appeared in 1960. It was the result of some early AI efforts by John McCarthy. And he had the belief that in order to make a machine be as intelligent as a person, it needed to be able to manipulate lists of symbols recursively. And so that was a key capability in his design. And unfortunately, Fortran didn't have recursion, and so they couldn't use it. So one of his students wrote the first Lisp interpreter in machine language. Ironically, while Lisp was intended to help create artificial intelligence, it's actually Fortran's numerical libraries which are at the heart of today's modern AI advancements. And while Fortran was created to help make computation easier, actually Lisp is better at analyzing computation because it's closer to the lambda calculus. And so that's kind of an interesting twist between those languages. So the third language was Forth. And so this was introduced by Chuck Moore in 1970. And he spent the previous 10 years developing it as a personal utility for writing programs. And the first problem that he was trying to solve, why not Fortran? Well, he was writing in Fortran. It's just that every time he would make a change, he'd have to recompile this huge, Fortran program. And he kind of got tired of that. over over a while. And so what he did was he built something that essentially where you could script things at near runtime and act as a command dispatch language. And so instead of having to recompile like a whole program, he could do a lot of these things in real time. And so that was one of the big benefits for him. But gradually, Forth began to reflect Chuck Moore's philosophy on how to write good code. In particular, he felt there were too many layers in between the programmer and the machine. And each of these layers was a source of complexity and a source of error. And so what he wanted was, he wanted Forth to be the top, bottom, and middle of the application. And in fact, he created some actual silicon that just runs Forth on it. And so he can just get away from even the instruction sets of those CPUs. So he wanted programs to be as simple and as elegant as possible. The strengths of Forth play into that, and we'll talk about that a bit more later. So the next language we'll talk about is C. So Dennis Ritchie and his Skunkworks team at Bell Labs created C in 1972. And so the question they need to answer is, why not Fortran? Or Lisp, but in particular, why not Fortran? Ritchie's team was trying to build a simpler alternative to this mammoth Multics operating system project that Bell Labs was working on. And they called their project UNIX to poke fun at it. And they originally did want to use Fortran to build the operating system and the utilities. But turns out that it's really complicated to build a Fortran compiler. And so, it was too difficult. And so they decided to start with a simpler language called BCPL, but that was also too difficult. And so they pared that down to make it much simpler, and they called that language B as a joke. And they got it to work, but the resulting programs were really, really slow. And so Dennis Ritchie kind of looked at this and then shored up, the parts that were bad, redesigned other parts, eventually made it so that it was a very performant language. And to continue that joke, he called it C. And so, so why not Fortran? Well, they did want Fortran. They couldn't get it, couldn't have it. But it turns out that C was actually a lot better at building operating systems than Fortran would have been. It was basically designed to do it. And so it was really the purpose behind C was to build Unix. And that's why it's an awesome language for that. Okay, the next language we'll talk about is C++. The question it had to answer is, why not C? So Björn Strustrap of Bell Labs released C++ in 1985. And 5 years previous to that, he was trying to model distributed computing, so using the object-oriented ideas from Simula. But Simula was too slow to be taken seriously for any type of real work. So what Strustrap did was he started with C, which was highly performant and excellent at least single operating system work. And he added object-oriented concepts of Simula via a preprocessor. And so originally C++ was like a little meta language that sat on top of C, the host language. And so that's kind of where C++ came from. Eventually C++ became its own language, but as time went on, it grew in complexity because it had to model an ever-increasing range of problems. And object-oriented programming and object-oriented design tends to get complicated as you go on, because at some point, especially when generics show up, you're trying to have some consistent type system and yet have the pragmatic capabilities of just having a list of things. And in order to make all of that work out in the end, you need a lot of complexity and a lot of overhead to make sure that everything lines up. But C++ is extremely popular today. Maybe not as popular as it was in the late 80s and 90s, but it is still the language of choice for graphical and GPU computation, and also in distributed computing. It has a lot of leverage there. And so the original design, the original reason for C++ is still where it shines today. Okay, the next language that I'll talk about is Haskell. And so Haskell is a different, we're like in a different domain now. So whereas Fortran and C and C++ and Forth, they're trying to solve real world problems, Haskell came out of a different domain. And so it was more of a research-oriented language, in particular, a functional programming language. And so it wasn't so much C and C++ that it had to contend with, but it was more of, why not Lisp, or why not ML, or why not Miranda? The reason why not those is that each of those languages had certain shortcomings in terms of, in particular, their purity. By that, I mean that when you have a pure functional programming language, you don't have any side effects. That you have functions and you can manipulate functions, but you don't change anything. Like you can, there's no state changes. It's just an expression of some mathematical relationships between things. And so a lot of those other languages had issues in that regard. And so Haskell was really designed by a committee of people that came together in the 80s to kind of figure this stuff out. And so it was designed to be the functional programming language to fix the problems with all functional programming languages. And so because of that, it has a very mathematical and rigid bent. It has a very powerful but also unforgiving type system. And its philosophy is correctness through functional purity. And people like to say that, once you get a Haskell program to compile, then it's correct. That's not true, by the way. But it is largely true that there's a lot of errors that go away when you model things in this way. It's also many coders' introduction to category theory, or at least monads, which is unfortunate because category theory is so much more flexible than Haskell would imply. But there you go. And we'll talk more about category theory later, especially in terms of Forthic. But as a language that teaches functional programming and its concepts, it is excellent. All right, so the next programming language we'll talk about is Python. So Python, why not C or C++? So in 1991, Guido van Rossum, the creator of Python, was working on a team that was building a high-level language called ABC, which was meant to be easy for novices to learn, much easier than C or C++. And so that's the rationale there. However, it's really hard to add functionality to it. And so over a winter break, Guido van Rossum was kind of playing around, and he wanted something that had the readability of ABC, but which was easier to extend. If you could extend it easily, you could build modules for it. If you had modules for it, then you could ship functionality with the language, so it would have batteries included. And so that was his goal. And he called the language Python after Monty Python. Yeah, and so it's become one of the most popular languages in the world. And it's really because of this combination of readability and extensibility and as batteries included mentality. So it's excellent for building lots of things. It's easy to get started with. There's just so much stuff that you can start doing out of the box. And okay, so that brings us to Forthic. So the name is kind of a spoiler, but I'll go through my reasoning for why I needed this language and the types of problems I was trying to solve and why I based it on Forth. So in 2018, I was building Python-based tooling for project managers at LinkedIn. These tools ran and were deployed on infrastructure that was designed for like really large-scale systems. And at first it's kind of fun. You're like, wow, this is neat. I'm building this thing. I'm deploying the thing on the same tooling and infrastructure that LinkedIn gets deployed on. But after a few deployments, I started to see what Chuck Moore must have felt in terms of all of these extra layers. It's not that it was creating bugs or errors or complexity. Well, it was complexity, but it was also taking a lot of time. So the types of programs that I built were things that needed to be tweaked. And so I'd build one thing, a program manager would see it and say, oh, they'd like the same thing, but with this a little bit different and that a little bit different. And so every time you had to do like one of these changes, you'd have to go through this whole process of redeploying something. It just felt really slow to me. And so I wanted to get to a point where kind of what Chuck Moore wanted to do. And so that was really the problem that I was trying to solve. And as I've been saying, the language that was closest to doing that was Forth. I didn't know that at the time, but that I ended up in the same place. But Forth out of the box wasn't really going to cut it, because Forth was designed to do numerical computation. It's terrible at string handling. And the types of applications that I needed to build needed to deal with lots of strings. You have JSON strings coming from different sources. You have to manipulate them. You have to construct JSON payloads to send out to other services. And so there's just a lot of string handling. And so Forth was really bad at that. The other problem with Forth is that, as I mentioned before, it wants to be the top, bottom, and middle of the application. I wasn't going to do that. I'm not going to build my own JSON parser or my own web server or my own, I don't want to do that. Like we have this stuff, like we have it, it's running on Python, some of it's running in JavaScript. I would rather just focus on the top of the app and let the bottom and middle be done by the host language. So I started with Forth, and I got rid of the parts I didn't like or need, and I designed it really just focusing on the top of the app. In particular, I made a design choice, and that the choice was that this language was going to be incomplete in some sense, that it would always need the host language that it was implemented in. So that was just something that I was going to accept. But what was nice about that is because it was incomplete, I could really have it focus on the top of the application. That it really let me almost physically separate high-level code from the low-level computation and simplify both sides. And the top layer of Forthic can run in straight lines. I don't have an if statement. I don't have loops. It has a more of a Haskell feeling in that sense, because we are dealing more with relationships between things and between, categories. And because of that, that top layer becomes very concise. And the host language layer is where the computation takes place. So what's nice about that philosophy is that it's also great at expressing solutions to problems mathematically. This isn't mathematically in like a lambda calculus way or something like that, or even in a Haskell mathematical way. But it's in a way where it's coding as transformation rather than coding as computation. And this coding as transformation idea lines up really well with category theory. And so category theory is, as I mentioned before, is extremely flexible. And Forthic has that same flexibility. And so instead of having this rigid view of types, objects, and relationships, you have almost this still mathematical, but fluid. And that fluidity is the thing that gives it its flexibility and tweakability. And this language wasn't Forth. It was something different, but it was like Forth. And so that's why I called it Forthic. So that's where the name came from. Yeah, so Forthic was influenced, as I mentioned, by the languages I've described here. Like Fortran, it was an abstraction above, but not above the machine, but above the host language, so similar to C++ in that regard. Its standard library was influenced by Haskell's standard library, so those same concepts, those same functional concepts appear in the Forthic global module. The Forthic module system was inspired by Python. I wanted it to be easy to extend, and so that was very important. And the Forthic syntactic simplicity comes from Forth, and this enables it, paradoxically, to express different and disparate types of coding paradigms simultaneously. So you can have functional, declarative, object-oriented, asynchronous, or anything you and your host language know how to do. You get it in Forthic, for free. And to me, that's huge because that lets you write code in the way that you need to write code. That lets you solve problems in the way that you need to solve problems. My goal in these videos is to teach you enough to get started, and in particular, by starting with existing applications and not having to worry about the details of the applications, but knowing enough so that you can tweak those applications, so you can get the benefits of a well-written Forthic application and a powerful Forthic application, but being able to make it your own by tweaking it. That's what we're going to talk about first. And so next time we're going to talk about how to get started with the Forthic repo. We'll talk about some of the basics of the Forthic language. We'll start going through some simple examples, and then we'll take it from there and see where we go. So thank you for your time, and hope to see you next time.